Good morning and welcome to the first session of numerical methods, Newton-Raphson method. In this session we are going to discuss Newton-Raphson formula, Newton-Raphson algorithm, and finally some sample problems using Newton-Raphson algorithm. This Newton-Raphson method is an iterative method to find solutions of algebraic or transcendental equations. Algebraic equations means an equation which involves a variable x or y and its higher powers and equal to some constant or 0. Transcendental equations are equations which involves transcendental functions like trigonometric functions, logarithmic functions, or exponential functions. This method converges rapidly with order of convergence too. That means Newton-Raphson method is a fast method and it gives approximate solutions within short time and within short epoch. The idea of Newton-Raphson algorithm is start with an arbitrary solution x0 and we improve the accuracy of this x0 using this iterative formula xn plus 1 is equal to xn minus f of xn by f dash of xn. That means next iteration is equal to current value of x minus current value of function at the point xn and divided by derivative of that function at the current value. So xn is the current state value or current approximation. Using the current approximation we find the next best approximation. Iterations will terminate when desired level of accuracy is reached. That means whenever these successive approximations becomes very same or their difference is very small, or xn plus 1 is approximately equal to xn, in that situation we can terminate this Newton-Raphson algorithm. To implement Newton-Raphson method in a computer, we can develop an algorithm like this. Start with an initial solution x0, find f of x and f dash of x at this point x0. Find next approximation using xn plus 1 is equal to xn minus f of xn by f dash of xn. If the difference between the approximations, the successive approximations xn plus 1 and xn becomes very small, then we will stop. Otherwise go to this iterative step. That is the procedure. So mathematically we can do this problem using a tabulation approach, but in computer we can use a for loop or while loop. So an example, consider this problem. Find an approximate solution of x cube minus 5x square plus 7 is equal to 0 corrected to 3 decimal places using Newton-Raphson method. So this is our function. So we'll call the left side as f of x. So f of x equal to x cube minus 5x square plus 7. So to complete the first step we have to start with an approximation. To get to the first approximation I am using bisection method. That means using intermediate value theorem, this function f of x is a continuous function, so it takes 0, that means solution, between within an interval which contains a point with a positive value and a point with a negative value. And so we find out a point at which the function gives a negative value. Here f of 2 is negative, so I can choose this 2 as a, and f of 1 is equal to 3, that is greater than 0, and therefore we can choose b as 1. So a is equal to 2, b is equal to 1, or a is the point at which this function is negative, b is the point at which the function is positive, and therefore we calculate x0 as the bisection of this interval, that is 2 plus 1 by 2 or 1.5. If this step is not mandatory, you can start with any x0. After successive approximations, the Newton-Raphson method converges fast to a better approximate solution within 5 or 6 iterations in a common way. So we start with f of x, x cube minus 5x square plus 7. Derivative of f is equal to 3x square minus 2 into 5, 10x plus 0, or 3x square minus 10x. Now we write the Newton-Raphson iterative formula. Xn plus 1 is equal to xn minus f of xn by f dash of xn. Here I rewrite xn like this minus this expression f of xn. Here we have f of x, so we replace x by xn in f of x. So xn cube minus 5xn square plus 7. And also in the case of f dash of xn, 3xn square minus 10xn. So we have a simple expression in terms of xn and powers of xn in this case. Now we can simplify this expression by cross multiplication. 3xn square minus 10xn into xn minus 1 into xn cube minus 5xn square plus 7 the whole divided by 1 into 3xn square minus 10xn, or xn into 3xn square is 3xn cube minus xn cube. 3xn cube minus 1xn cube is 2xn cube. Then minus 10xn into plus xn minus 10xn square minus 5xn square. So minus 10xn square plus 5xn square is minus 5xn square. Then minus into plus negative, so negative 7 the whole divided by 1 into 3xn square minus 10xn. So this is the Newton-Raphson iterative formula. That means next stage approximation xn plus 1 can be obtained from the current stage xn using this formula. So we form a tabulation table. The first column stands for iteration, that is n. Second column stands for current value of x, that is xn. Next column stands for next approximation using Newton-Raphson iterative formula. Xn plus 1 is equal to here 2xn cube minus 5xn square minus 7 the whole divided by 3xn square minus 10xn. Now we start with the x naught. When we put n equal to 0 here, x naught equal to 1.5 and substitute that 1.5 in this expression, I got 1.393939. So the next stage is x1. So from this is our x1, we rewrite xn here. Then we substitute this x1 here in this formula. I got x1 plus 1 x2. Then I write x2 here and substitute this x2 to get next stage approximation. But up to the second iteration we got xn and next approximation xn plus 1 are same. That is the advantage of Newton-Raphson method. Newton-Raphson method converges in a fast way compared to other iterative methods like bisection, secant method or regular fallacy, etc. So therefore an approximate solution corrected to 6 decimal places. See here 1, 2, 3, 4, 5 and 6. All the 6 decimal places are equal in this approximation, and therefore the 6 decimal place correct solution is x equal to 1.393099. Now we move on to next problem. We are going to develop an iterative formula to find the root of n. So formulate an iterative formula to find square root of n. Use it, calculate square root of 43 corrected to 4 decimal places. So we start with this root n. We have to find root n. In algebra, those things which are to be found we write x. So x equal to root of n. And so x square is equal to n. We simply avoid this root of n by taking square. So x square is equal to n. Now we write x square minus n equal to 0. That means right side is 0. Then left side expression is called f of x. So f of x equal to x square minus n. F of x equal to x square minus n. And therefore f dash of x is equal to derivative of this expression 2x. Now we rewrite xn plus 1 is equal to xn minus f of xn by f dash of xn using Newton-Raphson method. Now we substitute this f of x and f dash of x with xn in place of x like this. F of xn is xn square minus n. F dash of xn is 2xn. As in the previous problem, we cross multiply this expression and simplify. 2xn into xn, 2xn square minus xn square, that is plus xn square. Minus into this minus gives plus. So xn square plus n divided by 2xn. So xn plus 1 is equal to xn square plus n by 2. Xn gives an iterative formula to calculate square root of n. Okay. Then to find the next part, that is square root of 43. You have to calculate square root of 43. So n is equal to 43 here. So we replace n is equal to 43 in this expression and we form a table to find an approximate solution using iterative formula. To find square root of 43, just put n is equal to 43 in that Newton-Raphson iterative formula. That is, this n is replaced by 43 here. Then the table contains 3 columns: n, there is iteration, x, and the current value of approximation x, next approximation of x, that is xn plus 1. I start with an approximate value, the 6.2. You can start with any value, but I choose the 6.2 because this 43 is not a perfect square. We know 6 square is 36 and 7 square is 49, and therefore this third root of 43 will be in between 6 and 7. For convenience, I took 6.2, that's all. So next stage iteration, xn plus 1 is equal to, I put xn in this formula. So 6.2 square plus 43 by 2 into 6.2. So we got the solution. Then we take this value as next stage xn. Put this xn into xn plus 1. I got next level of approximation. When we continue this process up to the third level, we got xn and xn plus 1 are same. That means these two approximations are corrected to 6 decimal places, 1, 2, 3, 4, 5 and 6. So an approximate value of root 43 corrected to 6 decimal place is 6.557439. Commonly we mark the final value of xn plus 1, that is the more finer compared to the previous stage. So in this case both these values are same, so we boxed the solution. An approximate solution of root of 43 or approximate root of 43 is 6.557439. Next interesting problem is find an iterative formula to find 1 by n, to find the reciprocal of a number in an iterative way. As in the previous case, we write x is equal to 1 by n. We have to find this 1 by n. So 1 by n is an unknown. In algebra, it is represented by x. So x is equal to 1 by n. So the direct approach is we put 1 by n to the left. So x minus 1 by n is equal to 0. So f of x equal to x minus 1 by n. In that case, f dash of x equal to derivative of x, that becomes 1. So when we put 1 in this formula, there is no improvement in iteration. So remember, whenever you took x equal to 1 by n, you have to change it in the form n is equal to 1 by x. So we have 1 by x, the variable is 1 by x. Its derivative is minus 1 by x square. So the denominator will not be a constant. It is very important. So I take reciprocal of both these sides. So reciprocal of 1 by n is n, reciprocal of x is 1 by x. Then I take this 1 by x to the left side. So n minus 1 by x, I take it as f of x. So f of x equal to n minus 1 by x. Now we are going to use Newton-Raphson method. First step is find derivative of f of x. F of x is equal to n minus 1 by x. Its derivative of n is 0. Derivative of 1 by x is minus 1 by x square. Here is a negative. So negative into negative positive 1 by x square. So xn plus 1 is equal to xn minus f of xn divided by f dash of xn. That is our Newton-Raphson formula. And substitute f of xn and f dash of xn. I got xn plus 1 equal to xn minus n minus 1 by xn the whole divided by 1 by xn square. Here this is 1 by xn square, that is reciprocal of 1 by xn square. So this xn square come to the numerator. So xn minus xn square into n minus 1 by xn. They distribute this xn square into this bracket. Xn square into n xn square minus xn square into minus 1 by xn gives plus xn, that plus xn plus this xn 2xn. So 2xn minus nxn square. So this is the required iterative formula to find reciprocal of n using Newton-Raphson method. So next problem is solution of a transcendental equation. This equation is called a transcendental because it contains logarithmic function. As in the previous case, I take this 4.77 into the left side and then call it as f of x. So f of x equal to x log to the base 10x minus 4.77. Then here also I am using bisection. I am trying to find out a point a which gives negative value to this function f of x, and another point x which gives a positive value to this function f of x. Then here f of x is negative, so I took a is equal to 6, and similarly f of 7 is positive, and so this 7 is a positive argument. I call it as b is equal to 7. So x naught is equal to bisection of this interval with the limits 6 and 7. So 6 plus 7 by 2 equal to 6.7. Now I write f of x and calculate f dash of x. Here we have to take in one important point, x into derivative of this log to the base 10x. X into logarithm is 1 by x, but we have to take derivative of logarithm of e with respect to 10, changing the base rule, x into derivative of log is 1 by x. Actually, log to the base ex gives the derivative 1 by x. Here the base is not e, so we have to compensate it with multiplying by this factor. So x into derivative of the second function is 1 by x into log of e to the base 10 plus second variable, that is x into log x into derivative of x. Derivative of x is 1, so log to the base 10 x. The next term is minus 4.77, its derivative is 0. So we can simplify this expression, x and x get cancelled, so 0.4342925 is a value corresponding to log of e to the base 10 from a scientific calculator. So this step is very important. Usually people forget to multiply by this change of logarithm, change of base of logarithm. X into derivative of the second term is 1 by x into logarithm of e to the base 10 plus x into log to the base 10x into derivative of x, that is 1. Now we substitute the value of log to the base 10 e here. Now we write the Newton-Raphson iterative formula, xn plus 1 is equal to xn minus f of xn by f dash of xn. Substitute f of xn here, that is xn into log to the base 10 xn minus 4.77. Then f dash of xn. Here we have f dash of x equal to 0.4342945 plus log to the base 10x. So f dash of xn is simply obtained by replacing x by xn in this expression. So 0.4342945 plus log to the base 10 xn. Simplifying this expression, as in the previous case, we cross multiply and simplify. We get 0.4342945 xn plus 4.77 minus into minus plus whole divided by 1 into 0.4342945 plus log to the base 10 xn. This is the iterative formula to find out solution of this transcendental equation, x log to the base 10x minus 4.77. As in the previous case, we form a table with the 3 columns. First column corresponds to the iteration or epoch, the second one is the current value of x, and third column is the next approximate value of xn plus 1. So when n equal to 0, this x0 is 6.5. Then we substitute x 6.5 in this expression, we got next approximation. Then I choose this for the current approximation. Using this in iterative formula, I get the next iterated value. We repeat it in the third step, we got xn and xn plus 1. The approximations become same, corrected to 6 decimal places. Therefore, an approximate solution corrected to 6 decimal places is x equal to 6.083173. Instead of this 6.75, using the bisection, you can start with any value. Automatically, after 5 to 6 iteration, we got this result. That is the advantage of using Newton-Raphson method. Next problem is find a positive solution of cos x plus 1 equal to 3x using Newton-Raphson method corrected to 4 decimal places. Here also is a transcendental equation, but we need positive solution. We know that modulus cos x is always less than or equal to 1. So it is better to put this cos x plus 1 to the right side to get a positive solution. Okay, so f of x equal to 3x minus cos x minus 1. As in the previous case, we use bisection. F of 0 is negative and f of 1 is positive. So I choose a as the point which gives the negative value, a is equal to 0, and b is the point which gives the positive value to this function. So b is equal to 1. So bisecting that interval, I got x0 is equal to a plus b by 2 is equal to 0.5. Now we start with f of x equal to 3x minus cos x minus 1. F dash of x equal to 3 into derivative of x is 3. Derivative of cos x is minus sin x, minus into minus plus, so 3 plus sin x. Now we write Newton-Raphson formula xn plus 1 equal to xn minus f of xn by f dash of xn. Substitute f of xn and f dash of xn here, and on simplification I got xn sin xn plus cos xn plus 1 by 3 plus sin xn. Now we create a table with the 3 columns. First column is iteration, second column is xn, and third column is the next approximation using Newton-Raphson, that is xn plus 1 is equal to xn into sin xn plus cos xn plus 1 divided by 3 plus sin xn. I put this xn to this equation, I got xn plus 1. I repeat, on the third stage I got almost the same value for xn and xn plus 1. So xn plus xn minus xn plus 1 or modulus of xn plus 1 minus xn, whatever it is, it gives 0. So this approximation converges and we got an approximate solution corrected to 6 decimal places, and it is equal to 0.6071016. So the important takeaways of the session are the Newton-Raphson iterative formula, that is xn plus 1 is equal to xn minus. Some people by mistake put plus in this instead of this minus. So remember, xn plus 1 is equal to xn minus f of xn by f dash of xn. Always ensure that this f dash of xn will contain variable. It will not be a constant. If this is a constant, then approximation will not converges. It will continue at the same value of xn. There is no change happens. In Newton-Raphson iterative formula to find root n and 1 by n, etc. We can extend the same method to find third root of n or n raised to 3 by 2 or anything like that for any positive integer n using this Newton-Raphson method. So this is all about the basics of Newton-Raphson method as a first topic of numerical methods in 4th semester classes. Okay, thank you very much.